Hello. Today we are going to need both our calculators and our reference tables. So first thing that I need you to do is to open up your reference table to the back of the first page and find the section labeled Kinetics. And next to these equations, I want you to write zero order next to this first equation on your reference table. First order next to this equation that uses the natural log. Don't worry, natural log, it's just a button on your calculator. Even if you didn't love doing logs in math class, you're fine. You have your calculator to help you out. And second order next to the 1 over a calculation, and then half-life next to our last calculation. So what we are going to use these for, we've got two ways to use them. One, they will help us figure out what the order of our reaction is. And then two, if we know the order, we can use these calculations to figure out the amount of time it would take for our reactant to change from a certain value to a different concentration. So again, make sure that you record that on your reference table. Okay, so first thing, we are going to do a lab where we will measure the concentration of a reactant over a certain amount of time. And then we will put that data into Microsoft Excel, and then we will produce some graphs. So we will produce a graph of the concentration of A versus time. And we will do the natural log of A versus time. And we will also do 1 over the concentration of our reactant versus a certain amount of time. And then we will graph those. Whichever graph produces a straight line, or with our lab data, closest to a straight line, that will tell us what the order of the reaction is. So let's say that we graph these and we get a line like that. That's not very straight, so our experiment or our reaction was not zero order. Let's say we get this, that's pretty straight. So since natural log is the first order calculation, that would tell us that our reaction was first order. And then also we would do our due diligence. We would do all of our graphs, and let's say that one was that. So again, not very straight. So our straightest line would tell us our order of our reaction. And also, your slope of your line will tell you the value of K. So this slope is negative, K must be positive. So we would just negate K, and then that would give us our value for K. So that is one way that we are going to use these equations. So as a review, first order reactions are dependent upon the concentration of a single reactant, and whatever that reactant does, that's what also happens to the rate. So if we double the concentration of our reactant, that will also double the rate. If you take the rate law through the magic of calculus, you will end up deriving that equation there. And again, if our reaction is first order and we graph the natural log of A versus time, it will produce a straight line. And that would then tell us that our reaction was indeed first order, and also that would give us the value of K, our rate constant. Now, once we know that our reaction is first order, and once we know the value of our rate constant, then we could calculate a bunch of other stuff. So we could take our initial concentration of A, let's say it's 0.1 molar. We could figure out how long it would take for the concentration to drop to 0.001 molar. Or, we could figure out after an hour what the new concentration would be. So we'll be able to do some calculations with that. Again, just to repeat that, if you take the rate law and do some differential equations, you'll eventually end up with that natural log equation. Again, if you graph the data, whichever graph gives you the straight line, that's going to be the order of the reaction. So in this particular picture, this is the graph with the straight line, or the straightest line. And since it's the natural log graph, it correlates to the natural log equation, which goes along with our first order reactions. So from the slope, we can get the value of K. So this would just be an example of that. You can see that that graph, that line looks nice and straight, and it's the natural log of the concentration. So that tells us it is first order. All right, so now we're going to do a quick calculation. So we have this reaction here. They give us the value of K. So we have the value of K at 800 degrees Celsius, because K will change when temperature changes. So we can only use this K as long as the temperature stays at 800 degrees Celsius. How long will it take for A to decrease from 0.88 to 0.14 molar? Okay, so because this is a first order reaction, that tells us that we need to go ahead and use that natural log formula. So natural log of the concentration of A at time t minus the natural log of A initially is equal to negative K T. So natural log of A at time t, so that would be the 0.14 minus the natural log of the initial concentration, so that would be the 0.88, is equal to negative K. K is 2.8 times 10 to the negative second per second. And then T is what we are looking for. So now we just pick up our calculators and do a little bit of math. So natural log of 0.14. Oops, hold on. Sorry about that. There we go. So 0.14 minus the natural log of 0.88. And I get negative 1.838 is equal to negative 2.8 times 10 to the negative second times t. So I'm going to need to divide both sides by the 2.8 times 10 to the negative second. Now my negatives are going to cancel out, which makes sense because obviously t has to be a positive value. We don't have negative time. All right, that gives me t as 65.65. We would want two significant figures, so it is 66 seconds. And we know that it's seconds because our value of K was per second. So if K had been per minute, then our answer would be per minute. All right, we are going to do one more example with this. So using the information that we had on the previous slide, so we had the original concentration of A was 0.88, and we had the value of our rate law constant as 2.8 times 10 to the negative second molarity per second. Using that information, we are going to plug in to our natural log equation and figure out what the concentration would be after 60 seconds. So pause the video and see if you can set up that calculation and then come back to check your answer. All right, so let's take a look at how this needs to be set up. First off, we're looking for the concentration after a certain amount of time. So we would be looking for the AT. So we would plug in our original concentration, 0.88, plug in K, which I accidentally said the wrong units. K was just per second because it's a first order reaction, times our 60 seconds. So once I then do the natural log of 0.88, that gives me negative 0.128. So then I have a negative minus a negative. So that's going to change me to be a positive. So that's how I got down here. And then I did the negative 2.8 times 10 to the negative second times 60. And that gave me negative 1.68. Now I need to get the natural log of A at time t by itself. So then I subtract 0.128 from both sides of the equation, and I end up with this here. Natural log of A at time t is equal to negative 1.8 approximately. Now, in order to cancel out natural log, we just use e to the x because that's the inverse of natural log. So then you do the concentration of A at time t is equal to e to the value negative 1.808. You put that into your calculator, and that gives us 0.16 for the molarity. That makes sense. We started at 0.88, 60 seconds went by, so our concentration has to drop. Obviously, if your concentration increased, that would be a major sign that something had gone wrong. Now, technically, with the way the problem is written, 60 seconds only has one significant figure, so we would need to round that 0.2 with the one significant figure. Last thing that we need to talk about with first order reactions. First order reactions follow follow half-life. So the time that it takes for half of the concentration to decrease is the half-life. So we did this in Regents Chem with nuclear chemistry. If we started with 50 grams of a radioactive sample, its half-life is the time that it took to end up with half of that. So if we started with 50 grams, after one half-life, we would have 25 grams. After a second half-life, we would have 12.5 grams. After a third half-life, we would have 6.25 grams, and so on. So half-life is the amount of time that it takes to lose half of the sample or half of the concentration. So for a first order reaction, we can figure out the half-life. So ln of 2, because of half, divided by k, will give us the half-life. If we do the natural log of 2, we get 0.693. And this is how we get the equation that's on our reference table. So if we know k and we know it's a first order reaction, we can figure out the half-life. So 0.693 divided by k will give us the half-life. So that's just a reminder of what our half-life graphs look like. Now this is not a straight line because it's not the natural log of A, it's just the concentration of A, and you see that it's decreasing by half as time progresses. All right, so now we have an example to do real quick. So we are looking for the half-life of N2O5 if its decomposition is a they should say first order reaction and has that value for the rate constant. So we just use our formula from our reference table. So we just do 0.693 divided by the value of K, and that will give us our half-life. Now, one thing to point out as I put this into my calculator is you don't want to miss an easy reaction or an easy calculation. So if they give you basic half-life data like 100 grams to 50 grams to 25 grams, you could figure out the half-life just by looking at the data. But back to this problem, once we put that into my calculator, then I get about 1,200 seconds once I round that. I just want to briefly mention one more thing about half-life is if looking at our data, we can see that it is decreasing by half at even time increments. That's a huge clue that we have a first order reaction. So I just wanted to briefly point that out so we can see that it takes 5 minutes for the concentration to drop by half, and then another 5 minutes it drops in half again, and so on. So that would be a very big clue that we have a first order reaction.